Yeah, so we begin with a discussion on representation theory as a part of the course MA538. The course is a representation theory of finite groups, but the first part of the course we will be doing finite groups, and the second part we will be moving on to Lie groups, specifically compact Lie groups, because the discussion of non-compact groups is decidedly more complicated than compact groups. Reason why the techniques simply carry over to compact groups is that the averaging process that we do in finite groups that simply carries over to the case of a compact group. We have a Haar measure, which is an invariant measure, and that's the reason why it goes through. So let's begin. So we begin with a sketchy introduction. Oh, I have to share the screen. Sorry. Yeah, thanks for informing me. Otherwise, I'll keep on talking. And can you see the screen now?
Yes,
Yeah. Yeah. So a sketchy introduction. I mean, my introductions are usually very sketchy. Reason why they're very sketchy is that the subject is way too vast for me to give a very comprehensive introduction to the subject. In fact, in about few pages, in about 20, 15 odd pages, nobody can do justice to a representation theory, even for finite groups. So formally, the subject of representation theory of groups originated with a problem contained in a letter from Richard Dedekind to G. Frobenius on factorizing what is called the group determinant. I'm going to explain to you what the group determinant is very soon. But this is for general finite groups. Traces of representation theory, traces of special instances, particularly for abelian groups, go back to Gauss in his Disquisitions, Arithmetic, his most celebrated book on number theory, which was published in 1801, I believe, and Lejeune Dirichlet in his proof of the infinitude of primes in arithmetical progression. Characters of abelian groups were used both by Dirichlet and by Gauss. And the law of quadratic reciprocity was proved by Gauss in 1796. Gauss offered several different proofs. I believe he gave seven or eight proofs of the law of quadratic reciprocity. The law of quadratic reciprocity says that if P and Q are distinct odd primes, then Q by P, this is a Legendre symbol, the bracket A upon P. The round bracket A upon P. What is the meaning of round bracket A upon P? A is relatively prime to P, P is a prime number. Then this round bracket A upon P will be called 1 if A is a perfect square modulo P, and it is minus 1 if A is not a square modulo P. What do I mean by that? Look at the field ZP. In this field ZP, is A a perfect square or not? If it is a perfect, A is not 0, of course. If A is a perfect square, you will say that A upon P is 1. If A is not perfect square, you will say A upon P is minus 1. So law of quadratic reciprocity is basically Q upon P, Legendre symbol with P upon Q is minus 1 to the power P minus 1 by 2, Q minus 1 by 2. And this is a very celebrated theorem in number theory, can be recast in the language of character theory of abelian groups. And you won't see any representation theory in most of the proofs that you will encounter in elementary number theory. For example, you can look at Nevin Zuckerman's book on Introduction to the Theory of Numbers, or better still, look at Baker. My favorite book on elementary number theory is Baker, Alan Baker, A Concise Introduction to the Theory of Numbers. There are many. In fact, you can look at Hardy and Wright. There are plenty of books on elementary number theory. If you pick up any of these elementary number theory books, you're unlikely to see any representation theory out there. The key observation was made very late in 1872 by Zolterov that, again, A is relatively prime to P. So A is relatively prime to P, and you look at the field ZP, and you remove the zero element, and A is a non-zero element in a field, and so you multiply all the elements of ZP star by A. You will simply get the same elements but in some other order. And that is you get a permutation of the elements of ZP star. You get an element, you get a permutation. That permutation will have a sign. It either is an odd permutation or an even permutation. And the sign of that permutation is exactly matches with the Legendre symbol A by B. This important observation was made by Zoltarov, who gave an alternate proof of a new proof of the law of quadratic reciprocity. This has been generalized considerably by Duke and Spears in their paper which appeared in the monthly, and they generalized it to arbitrary finite abelian groups. And the law of quadratic reciprocity became the classical law of quadratic reciprocity became a very special case of the general theorem that they proved. So, subject of representation theory can be approached from several different viewpoints. One of them is that it's a generalization of classical Fourier analysis. So, loosely, one could say that representation theory of groups is non-abelian Fourier analysis. This is a viewpoint that we shall be maintaining throughout this particular course. The later part of the course, in the second half of the course, the latter part of the course, there will be a slant towards a Fourier analytic perspective. Although analytic technicalities will be kept to a bare minimum, let's begin by recalling two classical theorems in Fourier analysis, the Fourier series and the Fourier Transform. So, I've given a footnote. So, Fourier analysis with all the analytic apparatus will be developed in the next semester. I am teaching Fourier analysis in the next semester. So, start with the group of unit complex numbers, a circle. And the circle is a compact group. And so, when you have a group, you look for continuous homomorphisms. It's an abelian group. So, you look for the group homomorphisms from T to C star. And it's not a good idea to look at all possible group homomorphisms. Since it's an infinite group and it's a compact group, you should be asking for continuous group homomorphisms. So first of all, because T is compact, the image is going to be a compact subgroup of C star. Now, first exercise is to prove that a compact subgroup of C star is going to be contained in T again. Well, you take an element. Suppose for example, the image is not in T. Then the absolute value is either bigger than 1 or less than 1. If the absolute value of A is less than 1, the absolute value of 1 upon A, look at phi of 1 upon A, that absolute value will be larger than 1. And look at its powers. And then these powers will go off to infinity. How can that happen? Because the image group is compact. So with a little work, you will be able to show that the complete list of continuous group homomorphisms is basically e to the power int, or psi and z equal to z to the power n, where z belongs to. This is a very nice exercise, and that's the first exercise in this course. So now we can ask whether a given function f from T to complex numbers can be written as an infinite series. So classical Fourier analysis asks whether an arbitrary function from T to C can be written as an infinite series, summation ck psi k. These psi's are called the characters of the group T, or the compact abelian group T. And so you're writing an arbitrary function as an infinite series of characters. Okay. Of course, certain tricky questions will come up. What do you mean by this infinite series? Does the series converge pointwise? Does the series converge uniformly? Does the series converge in L2? Does it converge in the sense of distributions? These, of course, are analytic details, and that will be taken up elsewhere. Now, let us look at the other abelian group, the group of real numbers under addition, and now look for continuous group homomorphisms from the real line to C star. Now, this real line is not a compact group, so now the image will no longer be in a circle, but I can take a phi, it is mapping into C star, so I can look at phi upon mod phi. I can normalize it, I can divide by the length, and this psi is again going to be a group homomorphism. And now the next question is, find out what are the continuous group homomorphisms from the real line to T. It's not difficult exercise to, and you would have figured out that these continuous group homomorphisms are e to the power ix chi, where chi is a real parameter. So let chi vary through the real numbers or all possible real numbers. So you've got a continuous family of continuous group homomorphisms. Again, the exercise is to prove this claim. Here is an optional exercise and a slightly more difficult exercise. Show that instead of continuous group homomorphism, if I ask what are the measurable group homomorphisms, there is a measure on the real line, the Lebesgue measure. And with respect to Lebesgue sigma algebra, you want the function phi to be measurable. So if I drop continuity and ask for measurability, the result will be the same. Of course, if I drop measurability also, then it is no longer true. There are non-measurable group homomorphisms which are not of this form. And the next question is, can you think of any? Now what happens, the same question, a fairly general function from R to C, can you expand it as a superposition? That's a superposition, right? This particular thing. The infinite is a linear combination. Can it be written as a superposition of these characters? So e to the power ix chi is a character and its coefficient is f hat of chi, and you want to recover f as a continuous superposition. And this distribution of amplitudes f hat chi is called the Fourier Transform of f. And 0.3 is a familiar Fourier inversion theorem from classical Fourier analysis. Again, we can't, because the detailed analysis of this problem is subject of another course. Then we take finite cyclic group. Now take G is to be a finite cyclic group of order n, and we want to ask for the continuous. Then no continuity. It's a finite group, so the topology is a discrete topology. So everything will be continuous. Every function will be continuous. So you want a group homomorphism, and that group homomorphism. So how do I? This is a finite cyclic group. So it is generated by the. I can think of this G to be the. It has a generator. It has a generator. Let the generator be zeta, and I can send the generator to some place. Since zeta has nth root of zeta is 1, since zeta has order n, the image phi zeta must be one of the nth roots of unity. And so I send phi zeta to x of 2 pi I k by n, where k is any one of the choices from 0 to n minus 1. And each of these choices will give me a group homomorphism. And there are n group homomorphisms. And these group homomorphisms I can multiply. If phi and psi are two group homomorphisms, then phi psi, pointwise multiplication, is also a group homomorphism. So set of all group homomorphisms from G to C star is a group, is again an abelian group under pointwise multiplication of functions, and it has again n elements, and it turns out that this group is also a cyclic group. This group is called the dual group. The set of all group homomorphisms from G to C star is called the dual group. The dual group is isomorphic to G. Now one can take it one step further, and one can ask for finite abelian. Every finite abelian group is a product of cyclic groups, and I can take it one step further. I can take a finite abelian group, and I can take the set of all group homomorphisms from G to C star, again under pointwise multiplication as above, and again I get the dual group G hat, and the G hat will be isomorphic to G. Okay, now because a finite cyclic group, because a finite abelian group, the G hat and the G and G hat are isomorphic. This isomorphism is not canonical. You will need to fix a generator or a set of generators. Without fixing a set of generators, you can't establish this isomorphism. Any questions so far? So now, what about the set? Now, do the set of all group homomorphism from Z to T? Now, Z is an infinite group. Z is an infinite abelian group, non-compact, but it's a discrete topology. So you can have all possible. So every function will be continuous. So you can ask for all group homomorphisms from Z to T. Will this form a group under pointwise multiplication? Is this group the dual group? Is this dual group a familiar group? Of course. So what is the dual group of T? The dual group of T is what? I have this list of Z. Dual group of T is Z. and the dual group of Z will be T. So Z is an infinite, T is a compact group, the dual group is discrete, Z is discrete, and the dual group is compact. Whereas if you take the real 9, the story is very different. The dual group is again reals. Okay. But that is analysis, harmonic, abstract harmonic analysis. Now, suppose G is a finite cyclic group and F is an arbitrary function from G to C, then can you express this arbitrary function as a superposition of characters? Elements of the dual group are called characters. Abelian. I emphasize we are in the abelian setup. When you look at non-abelian group, there will be some technical complications will arise. We will see it in a minute. So, of course, I'm going to list the characters, and the first one, C1, will be the trivial group homomorphism. All elements go to 1. So now we want to expand this F like this. So here in this equation 0.4, I'm going to do a very simple thing. I'm going to put Z equal to 1, omega squared, omega to the power n minus 1. I'm going to get n equations. And I got n equations in n unknowns C1, C2, Cn, and I just have to solve them. And so to solve them, I'll have to look at the determinant of them. The determinant, it doesn't involve C, doesn't involve F. It only involves the characters evaluated at the roots of unity. And you can think of whether this determinant, there's a routine exercise to prove that this determinant is non-zero. And so you can uniquely solve 0.4, you can find out the CK. This is the discrete Fourier transform, the fast Fourier transform, and you probably want to look at it. So it will be a very, for example, you can begin by looking at it in Gilbert Strang's book. So let us begin with the first definition. Given an abelian group G, a character, I again emphasize, here my group is abelian. A character is a group homomorphism phi from G to C star, with additional hypotheses such as continuity in case G is an infinite group endowed with a topology, such as the group of real numbers or the group of circle. Through these examples, we see a pattern emerging. What is the pattern emerging of expressing a general function as a finite, infinite, or continuous superposition of characters? So these characters are in some sense the building blocks. They're the atoms, and I want to express a very general function as a superposition of these building blocks. This kind of Fourier decomposition has met with great success in the analysis of many problems in PDE's physics and number theory. Okay. The case in point is the group of prime residue classes modulo. Okay. So let us look at, let n be a natural number. We are going to assume that n is strictly bigger than 1. So, and I'm going to look at the group of prime residue classes modulo n. There's a finite abelian group. It may not be cyclic. If n is 17 or 19, 23, 29, it will be cyclic. But when n is 8, it is not going to be cyclic. When n is 10, it will be cyclic. So do you know when will it be cyclic? When will Zn star be cyclic? For which n's? Yeah. N is a prime, it will be cyclic. I said n it will also be cyclic for n equal to 10, but it will not be cyclic for n equal to 8. Tricky question. Okay, I'll give you the answer. If n is a prime, it will be cyclic. If n is a power of a prime other than 2, if n is a power of a prime other than 2, it will be cyclic. If n is 2 times p to the power of a prime, where p is an odd prime, it will be cyclic. So this is the all. These are the only cases where it will be cyclic. Okay. I mean, it's not difficult to prove this theorem. In fact, it's very elementary. The proof is elementary but slightly lengthy. and not interesting for us at this moment. Anyway, so it may not be, what I'm trying to say is that it may not be a cyclic group. Never mind, let it not be a cyclic group, it's an abelian group. And so we have the set of characters, right? It's a character group. Now this chi, this character chi, this group homomorphism from G to C star is defined for prime residue classes. That is when the GCD of M and N is 1, it is defined. What happens if the GCD of M and N is not 1? You simply declare it to be 0, just for convenience. So this character has been defined for all Zns. And now you define chi tilde to be chi composed with eta. So if you take an integer m, you simply define chi tilde of m to be chi of m bar. That is a composing it. That's all. So now we got the, and I'm going to drop this tilde. I'm going to drop this tilde, and I'm going to just simply this this chi composed with eta. I'm just going to call it chi. So now we got a mapping from Z to C. Except that this mapping chi will take the same values. It will take the same value at 1. Suppose, for example, suppose my number n is say 5. Then any two integers m1 and m2 which are congruent modulo 5, the chi value will be the same. That's the only thing. It's periodic. Periodic with period n. So now you got this function from Z to C. As you all know, I mean, in elementary transform analysis, when you have a sequence of numbers, you encode the sequence inside some holomorphic function. Suppose I give you a sequence A0, A1, A2, A3, dot, dot, dot. You immediately write down the generating function. A0 plus A1Z plus A2Z squared plus dot, dot, dot. It's a formal, if the power series converges, you get a holomorphic function. If the power series doesn't converge, you still get what is called as a formal power series. So the set of formal power series, though it may not have any analytical meaning, it has got an algebraic meaning. Algebraically, it makes perfect sense. It's called the ring of formal power series. It's a perfect bona fide object in algebra. But here we don't encode it, we don't do this, we don't take the power series. That is called the Z transform in analysis. But we don't take the power series. What we have taken is that we have taken the sequence, say, let us say C sub n, chi m, it doesn't have to be chi m, it can take any sequence of positive natural numbers, say C1, C2, C3, dot, dot, dot. So Cm by m to the power s. Cm by m to the power s. Instead of a power series, I've done something else. This object is called the Dirichlet series. So now I'm looking at the Dirichlet series corresponding to this character chi. And this particular object, because its chi is bounded, because it's periodic, no? So this infinite series will converge when for real part of S is bigger than 1. And it will define a holomorphic function. And this holomorphic function is the Dirichlet L function. So, any questions? Dirichlet L function clear? Is it clear it should be holomorphic?
Sir, this is holomorphic in S?
Holomorphic as a function of S. In the right half plane, real part of S bigger than 1.
I see.
So it is holomorphic in this right half plane. It's called the Dirichlet L function. Dirichlet used this function in conjunction with character theory in the proof of his famous theorem that if you take an plus b, when n is a natural number bigger than 1, in the sequence an plus b, where b and a are relatively prime, if b and a have a common factor, if a and b are both even numbers, then of course everything in this business will be even and not interesting. So a and b are co-prime. A and b are co-prime. Then this arithmetical progression has infinitely many primes. The details can be found in several books on number theory. An elementary book on number theory is Tom Apostol's Analytic Number Theory. Or you can look at the web notes of Monson. Dirichlet's proof is one of the greatest triumphs for character theory of abelian groups. I mean, there cannot be any two ways about it. The character theory already began to enjoy great triumphs in the middle of the 19th century. Now what happens is that let us now begin with non-abelian groups, finite groups, the most basic ones from the point of view of group theory. So the finite groups, in some sense, finite groups are built up out of simple groups. When is a group said to be simple? A group is said to be simple if it has no non-trivial normal subgroups. That is, G is said to be simple if the only normal subgroups are G and the trivial group. So a group of order 7 will be simple because it has no subgroup other than the whole group and the trivial group. The identity singleton, that's a subgroup, and the whole, because it doesn't have any subgroups at all. In particular, it doesn't have any normal subgroups, and prime groups of prime order are simple. And that's only, and as far as abelian ones are concerned, that's it. That list is over. What are the non-abelian simple groups? Any suggestions? Non-abelian simple groups. The smallest non-abelian simple group has order. Hello, guys. This is something that everybody should know, whether you're doing algebra or number theory or topology or analysis. This is something that everybody has to know. 60. 60. It is A5, the alternating group on 5 letters. This is the simplest non-abelian group. So again, what is a simple group again? A group is said to be simple, finite groups right now. A group is said to be simple if the only normal subgroups are the whole group and the trivial group. Okay. There are no proper normal, there is no proper normal subgroups. Now suppose I take a simple group. Suppose I take a, and these simple groups are the building blocks in group theory. Groups are constructed in some way out of simple groups. How? That's group theory. That's quite advanced group theory. It's called the theory of group extensions. So we will not get into that. Just believe it that they are. So understanding the simple groups and classifying them has been one of the greatest and one of the greatest problems in algebra. Has been understanding and classifying simple groups. So let us suppose take a simple group, simple non-abelian group, and let us take a group homomorphism from G to C star. The kernel of this group homomorphism is a normal subgroup, right? Kernel is always a normal subgroup. Can the kernel be trivial? If the kernel is a singleton, that means that phi is an injective map. That means that G is sitting inside C star as a subgroup. But G is non-abelian and C star is abelian. So you can't, the image. So image cannot be but the phi is an isomorphism between G and its image. And the image is a non-abelian. How can an abelian subgroup have a how can an abelian group have a non-abelian subgroup? Contradiction. So kernel cannot be one. So kernel has to be the whole thing. The kernel is the whole thing. So the kernel is the whole of G. The kernel is the whole of G means everything is going to 1. So the function is identically 1. Uninteresting. It is the most least interesting group homomorphism. So if you take a simple group and if you look for group homomorphism from G to C star, you only get the trivial one. So we already see a severe paucity of the basic building blocks. So for us, when you look at the abelian groups, the group of the circle, the group of real lines, finite groups, we looked at characters. And we used and we said characters are a group homomorphism from the group to C star. That was our starting point. And we had enough characters. We had a group of characters. The dual group was rich enough, and an arbitrary function could be written as a Fourier expansion in terms of characters. The moment you go to non-abelian groups, all hell's let loose because there is a severe paucity of characters. Is this clear so far? Already we begin to see a very serious problem emerging. So the idea of defining a character as a group homomorphism from G to C star won't work, because if G is a simple group, the only such object is a trivial object, a constant function one. So obviously, constant function one is severely deficient to produce for allowing an arbitrary function to be expanded as a Fourier series. So now, what happens to rectify this problem? It's very, for a modern student, you will say it's a very easy to rectify. You say that C star, what is C star? C star is group of all invertible 1 cross 1 matrices. So why are you bothered about 1 cross? You take the group of all 2 cross 2, 3 cross 3, 4 cross 4 invertible matrices. So take a fixed K, look at GLKC. And so C star is GL1C. So you have been looking at group homomorphism from G to GL1C. Instead of GL1C, allow GL2, GL3. Take a fixed K and allow group homomorphisms from phi to GLKC and call them call them. Don't call them characters, because that's not the definition of character, but you have to go a step further. So look at group homomorphism from G to GLNC, where N is fixed. Now, the N has nothing to do with the order of the group at the moment. Clear? That is called a representation. So a representation is a group homomorphism from G to GLNC for some N. This N is called the degree of the representation. So is this clear? How you can go from the abelian case to the non-abelian case? We saw that there is a very serious roadblock. There is a paucity of characters, and this deficiency can be overcome by allowing the target group to change from C star to something more complicated. So far, so good. But one thing is that, so I have given you the definition. Now once you given a definition, let us look at some examples. Now let us take, what is the simplest non-abelian group? The smallest non-abelian group is a symmetric group on 3 letters, a group of order 6. So now so you should start with the easiest one. So from the symmetric group on 3 letters, what are the group homomorphism into C star? The trivial one, everything constant function 1. That's one group homomorphism. We have another group homomorphism. Take a permutation and tell me what is the sign of the permutation. The sign of a permutation is a group homomorphism from S3 to C star. You got one more. Is there any more? There is no more. There are no more group homomorphism from S3 to C star. You can prove that these are the only ones. But we can do something better. What about what is S3? S3 is basically you can take an equilateral triangle. 3 vertices, 1, 2, 3. And rotate the equilateral triangle by 120 degrees. 1 goes to 2, 2 goes to 3, 3 goes to 1. Rotate it by 240 degrees. You got one more. So write down the matrices of these things. So you got 3 matrices. You don't rotate it at all. Just the 2 cross 2 identity matrix. Rotation by 120 degrees. Rotation by 240 degrees. 3 matrices you got. And then you can take the equilateral triangle. Correct. Place one vertex on the y-axis and the other 2 vertices on the x-axis, and do a reflection along the y-axis. That's a symmetry of the equilateral triangle. And do for the other. So there are 3 axes of symmetry, and there are 3 flips. But you can write down matrices for all of them. So I given you a group of the symmetries. So the group of the symmetry group S3 can be realized as the group of symmetries of a equilateral triangle. So I can realize S3 as a group of 2 by 2 matrices. It is, in other words, S3 is a subgroup of GL2R. And GL2R is sitting inside GL2C. Therefore, I've got a degree 2 representation. It's a subgroup, so it's a group homomorphism from S3 to GL2C. So I got 2 degree 1 representation. It was a trivial. Target space is C star. everything goes to 1. The target space is C star, a permutation mapped to a sign of the permutation. Third one, the target space is GL2C. And then you got, and I described the degree to represent this. How many I have given you? 3. Now this number 3 is very interesting because the symmetric group has 3 conjugacy classes. The symmetric group has 3 conjugacy classes. The number of conjugacy classes exactly seems to match with this number, and it is not an accident. Okay, so a class function. So take a group G. A class function in a group is a complex function f from G to C, which is constant on each conjugacy class of G. Sign of a permutation is an example of a class function, because if 2 permutations are conjugate, they'll have the same sign. Take, for example, the group to be GLNC. Look at the function A going to trace of A. That's a class function, right? 2 matrices which are conjugate have the same trace. Conjugacy in the context of matrices. The context of matrices, you don't use the word conjugacy, you use the word similarity. Conjugacy in the context of matrices is called similar matrices have the same trace, similar matrices have the same determinant. So the trace and the determinant are examples of class functions. Other examples of class functions on matrices?
So sum of k by k
Principal minus. Sum of the k by k principal minus is an example of a class function. And k is 1, you get the trace. When k is n, you get the determinant. And when k runs from 1 to n, you get a whole bunch of them. You get n of them, and that's all. Any other class function will be a polynomial in these things, or a function of these. These are the building blocks. Now, trace is the simplest because a trace is a linear transformation. Determinant is more complicated. Determinant is not linear. So, and trace is the simplest linear map that is conjugacy or a similarity invariant. It is the simplest non-linear, non-trivial function from MNC to C such that phi of P inverse AP is the same as phi of A. Determinant is also a function, but it's far from being linear. So now let us define the character of a group representation. A representation is a group homomorphism rho from G to GL and C. And the character of a representation is trace of rho. Now take the map. So you got this mapping G to GL and C. And from GL and C to C, you got the trace, the map. Take the composite. This composite function is called the character of this representation. Now this trace is not a group homomorphism. Here, remember, this is a multiplicative group, and trace is a linear transformation. So this trace of AB is not going to be trace A plus trace B. That's wrong, terribly wrong. So trace is no longer, so trace rho, the composition is no longer a group homomorphism, but it is an example of a class function. It's an example of a class function from G to C. Correct? If G is abelian, then if G is abelian, what are the conjugacy classes of an abelian group? Singletons. So conjugacy classes are all singletons. And so every function is a class function. Every function is a class function. Is this clear? So for an abelian group, all functions are class functions. So our problems in Fourier analysis can be reformulated as follows. Suppose f from G to C is a class function. Can we express f as a linear combination of summation C alpha trace rho alpha, where this family of rho alphas is in some sense a minimal set of representations, a kind of a building blocks of our theory? Question: do such minimal building blocks exist? Are they unique? Are they finite or infinite? Up to equivalence? Is there a notion of when would 2 representations be considered to be the same? Can we form, suppose there is a notion of equivalence, then we will pick one one representative from each equivalence class and form a parliament consisting of one member from each of these atoms. How do we go about finding such a set of representatives? So these are the questions in representation theory. So representation theory is in some sense non-abelian harmonic analysis. In harmonic analysis, you expand a general function as a superposition of something. Here, you can't work with general functions. Here, you need to work with class functions. So, a class function f can be expanded as a superposition of trace rho alpha, where rho alpha is a certain family of representations of the group G, and they are what are called irreducible representations. And there's a notion of when are two representations considered to be the same, there's a notion of equivalence, and from each equivalence class we'll pick one representative and we'll form a parliament of representatives. Okay, and such for a finite group, such a parliament will exist. It is finite in number. For a compact group, it may not be finite in number, but they are finite dimensional. Is it clear what the central problem in representation theory is?
Yes.
So,
Yeah.
yeah, I was asking about the expansion of the class functions as trace of the irreducible representations. What did you say? For finite groups?
For finite groups, you can find a finite family of irreducible representations. Rho 1, rho 2, rho 3, rho 4, rho k. Okay, such that this can be done. And each of these rows is a irreducible representations. So I can find a parliament of irreducibles. For the symmetric group, one irreducible representation will be the trivial representation. That all rho G is 1 for all G. There is one example. And then for the symmetric group, rho G equal to sign of the permutation, another irreducible representation. The third irreducible representation is the degree 2 representation that I talked about, matrices, displaying the symmetric group as matrices. So these are three. So here, so for the case of the symmetric group, I have a parliament consisting of three irreducible representations, and you take the trace. So each representation means that rho G will be a matrix. It could be a 1 cross 1 matrix in case of a trivial representation. It could be, or a sign representation. It could be a 2 cross 2 matrix. But you don't work with matrices themselves. You take the trace of those matrices. So take rho G, take the trace, and let the row vary over this parliament. You get a bunch of trace rho 1, trace rho 2, trace rho 3. There are three class functions, and any class function can be written as a linear combination of these three for S3. Is it clear?
Yeah.
So how do we go about finding it? So now let us let us see why the decomposition of this kind 0.5 is interesting. Why would we care about this kind of representation, the decomposition? Let us consider the problem of solving the Poisson's equation, say in the plane, or say the disk. Now, taking advantage of the rotational symmetry of the problem, we should be writing the Poisson's equation in polar coordinates, correct? And one is led to solving Laplacian of u equal to f on a circle. But on a circle, we know that the Laplacian is minus d2 by d theta squared. And so you take the function f as a superposition of these characters, correct? And then you seek the unknown also as a linear combination of these characters. And so our problem simply reduces to, and the uniqueness of representative we have, Our problem, you can immediately write down the solution. U equal to Cn by n squared e to the power I n theta. And that's it. That solves the Poisson's equation. The success of the method depends on two things. Representability of f as 0.2, that is a Fourier expansion, and uniqueness of the representation. The problem was simple because a group of symmetries. So for the Laplacian in the plane, I have taken in the plane R2. The Laplace's equation in the plane, the Laplacian in the plane, has a group of symmetries. A group of rotational symmetries is SO2R. And that's exactly an abelian group. It's a circle group. As soon as n becomes 3 or higher, the problem becomes difficult because the group of rotational symmetries, or the Laplacian in n, Rn, so the Laplacian is invariant under orthogonal transformations. So this SONR, when n is 3 or higher, is quite non-abelian. And of course, what about the wave equation? The wave equation, the group of symmetries of the wave equation, is a Lorentzian group. It's even worse. At least here, the saving grace is that the orthogonal group is non-abelian, but it's compact. The Lorentzian group is non-abelian and non-compact. So carrying out a program of solving, say, the Poisson's equation on a sphere instead of a circle would necessitate a study of irreducible representations of the group of SO3R, or more generally SONR. And so this is going to be done in the second part of the course. Following this, there's this book by Ernst Winberg, which has a very good introduction to these things. So there's an intimate connection between representation theory of compact groups and the study of special functions. One can also study
can the Noether's theorem be recast as a theorem in representation theory?
Which theorem?
Noether's theorem in physics.
Yeah, we will see. We will see how the Noether's theorem fits into this general scheme of things. It is a theorem on invariant theory, basically. Okay, so there is an intimate connection between the representation theory of compact groups and the study of special functions. One also studies non-compact groups, but the analysis gets harder when order of magnitude, because we know that when you have non-compact groups, you have to talk about spectral theory, and that spectral theory will involve continuous spectra, and that will require you to do this spectral measures and so on. So the more complicated, the more general you want, the more complicated the analysis will be. Identities between special functions, such as the addition formula, which at first seem strange and mysterious, become clear or natural and transparent in the light of representation theory. And there are applications to problems in theoretical physics. And I give you a reference to Willard Miller. And there is a book of Mackey which you should consult for the 31 illuminating essays on how representation theory enters into physics and number theory and probability theory. For the case of compact groups, the basic building blocks of the theory, called irreducible representations, are finite dimensional, and they're unique up to equivalence. Now, what do I mean by equivalence? We'll describe this in chapter 2. However, see, when something is, the statement that the irreducible representations of a compact group are finite dimensional and they're unique up to equivalence is the celebrated Peterbilt theorem. Now, though this theorem is beautiful, it raises more questions than it answers. So when something is unique, finding it explicitly is going to be a hard problem. And to discuss, okay, so SO3R is a compact Lie group. Its irreducible representations are finite dimensional. Tell me what they are. To tell me what they are, you will have to understand spherical harmonics. You will have to understand special functions. So special functions appear when you try to describe explicitly irreducible representations of compact groups. Okay, the principal theorem, that's the Peterbilt theorem. So among other things, the Peterbilt theorem says that a compact Lie group can be realized as a closed subgroup of SL, GL, and C. That is, compact Lie groups are matrix groups. For example, the group of spinors. Interconnections between representation theory and special functions have been used to great advantage in combinatorics, and development of quantum mechanics provided further impetus for the development of representation theory of compact groups. And the problem of group determinant. Now let us now leave this and go to the problem of group determinants and the early triumphs of the theory of non-abelian groups. We shall follow the treatment in T.Y. Lamb, and the paper of T. Hawkins is also recommended for this historical development. We have seen that the definition of a character of an abelian group as a group homomorphism G to C star is generalized to arbitrary finite groups by replacing C star, which is GL1C by GLNC, and then taking the trace of rho, the simplest linear class function. This transition was not an easy, direct, or routine matter. The story is beautifully narrated with clarity and vividness in Lamb's article. The story unfolds in the glorious era. Indeed, I'm inclined to say the romantic era, when letters exchanged between great mathematicians have given birth to deep mathematical theories of great import, and theories that have had a lasting influence for the development of modern mathematics. For example, the theory of the gamma function appeared in a letter from Euler to Goldbach. The problem of moments was discussed in a series of letters exchanged between Hermite and Stieltjes. The correspondences between Hardy and Littlewood is, of course, well known, and the letters exchanged between Richard Dedekind and Frobenius, which is of interest in the present context. Let us look at the problem of Dedekind. I'll just take a short. I'll just pause for a minute. My battery is running low. Just a minute, please. Yeah. So they consider a finite group G with elements G1, G2, Gn. To each Gi, we assign a indeterminate variable xi. So for G1, you assign the variable x1. For G2, you assign the variable x2. The variables are commuting variables. You're going to be looking at polynomials in these x's. Now, suppose you take a pair of ij, then Gi, Gj inverse, that will be again an element of the group, right? It's a finite group, Gk. So what we do is the following. When you take, so for each pair ij, you form this, you compute Gi, Gj inverse, calculate which Gk it is, and you put the xk, in the ijth position, and you get an n cross n matrix. So you get an n cross n matrix whose ijth entry is xk. So now you got a matrix whose entries are some x1, x2 are among x1, x2, xn's. This matrix is called the group, the determinant of this matrix is called the group determinant. Is this clear what the group determinant is, everybody? The concept of group determinant is clear?
Yes, sir.
Yeah? So take the group determinant, so first of all, form the group matrix, n cross n matrix. What is the ijth entry? Ijth entry is you calculate Gi, Gj inverse. That will turn out to be Gk, and put xk in the ijth entry and take the determinant of this. It's a polynomial. Question is that will this polynomial factorize? How do you factorize this polynomial? Now, as a first exercise, show that for any finite group, this group determinant will have x1 plus x2 plus xn as a factor. Is this clear? That x1 plus x2 plus xn will be a factor. Because when you multiply, what happens when you perform this Gi, Gj inverse? Fix the row index. The column index changes, no? And change the Gj. In other words, you're multiplying all the Gj inverses by a fixed Gi. you're going to get a permutation of the x. You're going to get a permutation of these things. So each row will involve. So an xk will be there in every row, and an xk will be there in every column. In every row, the xk has to appear somewhere. In every column, the xk has to appear somewhere. So is it clear? Is it clear that x1 plus x2 plus da 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 plus xn will be an eigenvalue? Suppose if I take the matrix and I multiply the matrix by the column vector 1 1 1 1 1, what happens? वो clear है क्या भाई?
Yes.
x1 plus x2 plus xn must be a factor. Correct? What about the other factors? Now, if you take the symmetric group, you'll also realize that x1, that if you take an xi and the sign of xi will correspond to gi, and gi is a permutation. It will have some sign. Put the sign also. That will also be a factor. So now another exercise is take the cyclic group of order 3 and write down this group determinant. You can actually do this exercise. And it will factorize into 3 factors: x1 plus x2 plus x3, x1 plus omega x2 plus omega squared x3, x1 plus omega squared x2 plus omega x3. You can please do the factorization for the cyclic group of order 3. If you try for the cyclic group of order 4, it will also factorize completely. You try to write the group determinant for S3. It's going to be a 6 by 6 matrix. But you should use Mathematica. If you want to do the problem efficiently. But if you don't want to use Mathematica, then you have to use some amount of cleverness. Be clever and avoid Mathematica, or save your brains for something else and simply let Mathematica do the hard work. It will factorize into 2 linear factors and a repeated quadratic factor. And the linear factors are, no prizes for guessing, x1 plus x2 plus da 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 plus xn, summation sine of gi times xi. And the third one will be a quadratic factor which will repeat itself. It's no surprise that these 3 factors are somehow related to the fact that we have 3 irreducible representations. Amazing. Now, of course, Dedekind proved that for every abelian group, it will factorize into linear factors. He tried this factorization for groups of small order, like the symmetric group and the quaternion group. And he communicated these things to Frobenius, and he intermittently worked on this problem on the group factorization of the group determinant. Of course, he didn't have Mathematica at his disposal. These were carried out manually. 10 years later, in a letter in 1896, Richard Dedekind communicated his results to Frobenius, who developed the theory of representations for a finite group, and the details of TY lab should be consulted. Now you might think that, what the big deal? Some problem somebody was curious to know and wrote a letter to somebody else, and he developed a theory and he cracked the problem. Why should the rest of the world be dancing up and down and learn this material? Let us see what happened. Soon after this, Frobenius developed the theory of representations. Within a decade of its inception, the theory of representations acquired another medal of triumph when William Snow Burnside in 1904 proved a very celebrated theorem that if you take a group of order PQ, it will never be simple unless it's a prime. If a group of order PQ, group of order P to the power A, Q to the power B, except in trivial cases such as B is 0 and A is 1, or A is 0, and then it becomes a prime power order. There's a group of prime order. So except for those trivial cases where A is 0, B is 0, A is 0, B is 1, A is 1, B is, except for these trivial cases, this group can never be simple. So this was a very major step towards the classification problem for finite groups, of finite simple groups. I said the classification problem for finite simple groups has been one of the most important problems which was investigated in algebra. Okay, so it took 70 years before a non-representation or a purely group theoretic proof was discovered, and that proof is much longer. You're probably still not convinced that representation theory is important and interesting. Let us look at more examples on the pervasive nature of representation theory. As we begin to see, representation theory has pervaded large parts of mathematics and physics. The reason for its omnipresence is that groups appear everywhere and they seldom appear as abstract entities, but rather through their action as groups of symmetries acting on a space. So you've got a topological space or a manifold, for example. You can talk about a group of diffeomorphisms on a manifold, or you may be talking about a group of symplectomorphisms or analytic automorphisms, whatever. That's how the groups appear. They don't appear as a set with a binary operation. That's not the way groups appear in mathematics. So when a group acts on a space S, we get an induced action on a space of functions. So the space of functions on S is LS, let us call it. Usually, LS will involve continuous functions, polynomials, L2 functions, whatever. So now if you take a function phi and you take a group element G, the group element acts. So now what you do is that this group, now I can take this function phi and I can cook up a new function G dot phi. What is this new function G dot phi? It is phi applied to G inverse of S. This way, the original group action, the group acting on a set S has been converted into an action of the group on a function space, which is of interest, such as the polynomials or L2 functions or something like that. And so that's a linear, and so this group action, phi maps to G dot phi. That's a linear transformation. Phi maps to G dot phi is a linear transformation. Call that linear transformation TG. That's an invertible linear transformation. And usually it will be a continuous linear transformation or a bounded linear transformation, whatever. So it will satisfy, it will have the appropriate qualities depending on the situation at hand. So this map G go to TG is then a representation of G in the vector space LS, because it is going to be a bounded, it's going to be invertible linear transformation. So this TG belongs to GL of the function space. The function space is a vector space, and the group of linear transformations of vector space to itself. In case you're looking at quantum mechanics or something, you might be interested in looking at bounded linear operators or whatever it is, as the case may be. And the function space will be L2. So it's so this is called the induced induced representation on the function space. So this is a two-step process, but it's a commonly appearing two-step process. And now classical invariant theory and the three pillars of modern commutative algebra. The group in classical. Maybe I think we should stop here and we'll continue this tomorrow, the remaining part of this lecture. Any questions?